Beneath a shell of ice stretching kilometers deep, an ocean larger than all of Earth's oceans combined has been hiding for billions of years. Europa, one of Jupiter's moons, almost certainly contains liquid salt water right now, kept warm by gravitational forces so powerful they crack the surface apart. Scientists believe this hidden sea has every ingredient necessary for life. But here is the problem nobody talks about. Getting to Europa is not the hard part. We could launch a spacecraft tomorrow and arrive within 6 years. The real obstacle is what comes after landing. Penetrating kilometers of ice in a radiation-blasted wasteland with no sunlight, no GPS, and no way to phone home might be the single hardest engineering challenge humanity has ever imagined. If you enjoy exploring the missions that could redefine our place in the universe, consider tapping that like button and subscribing. It genuinely helps this channel grow and lets me keep making content like this for you. Now get yourself nice and comfortable. Let's begin. In January of 1910, a man named Edward Emerson Barnard pointed one of the largest refracting telescopes on Earth toward Jupiter and carefully tracked the movements of its 4 brightest moons. Barnard had already discovered Jupiter's 5th moon 18 years earlier, and he knew this system better than almost anyone alive. But even through the finest optics of his era, the Galilean moons remained little more than points of light. But Barnard could not have imagined what lay beneath the surface of the smallest of those 4 worlds. It would take another 86 years and a spacecraft named after the man who first spotted those moons in 1610. It is a world concealing an ocean. The Galileo spacecraft entered orbit around Jupiter in December of 1995, beginning an 8-year campaign of observation that would fundamentally reshape planetary science. Among its cascade of discoveries, the most significant was evidence that Europa possesses a global subsurface ocean of liquid salt water, sealed beneath a crust of frozen ice that has persisted for billions of years. This was not speculation or wishful modelling. The evidence arrived from multiple independent instruments and multiple independent lines of reasoning, each converging on the same astonishing conclusion. Europa is wet. Right now. Beneath the cracked and fractured ice that makes up its entire visible surface lies more liquid water than exists across the entire surface of Earth. Every ocean on our planet, the Pacific, the Atlantic, the Indian, the Southern, the Arctic, all of them combined, still fall short of the volume estimated to exist in Europa's hidden sea. And that sea is not ancient history. It is not a relic from a warmer era long since frozen solid. It is liquid today, kept warm by forces so powerful they crack the moon's surface apart on timescales that make human civilization look like a brief flicker. Europa is small by planetary standards. Its diameter measures approximately 3,121 kilometers, making it slightly smaller than Earth's own moon. Its mass sits at roughly 65% of the moon's mass. If you could hold it in your hand next to the moon, Europa would look like the moon's slightly smaller sibling, pale and bright and superficially unremarkable. From a distance, it appears as a smooth, luminous sphere, one of the most reflective objects in the entire solar system. Its surface albedo approaches 0.67, meaning it bounces back about 2/3 of the sunlight that reaches it. That extreme brightness comes from water ice, a frozen shell that encases the entire moon like armor plating on a medieval warship. But look closer, and that surface tells a story of relentless violence. Europa's ice is not smooth. It is shattered, ridged, buckled, and reorganized in patterns that speak to a world in constant geological turmoil. Double ridges run across the surface like surgical scars, some stretching hundreds of kilometers in length. These paired formations rise above the surrounding terrain, with a valley running between them, resembling the features that form when ice cracks, separates, and refreezes on frozen lakes on Earth. Except, these ridges are kilometers wide. They tower dozens of meters above the surrounding plains, and they crisscross the entire moon in overlapping patterns that record millions of years of tectonic activity. Then there are the chaos regions, These are zones where the surface appears to have simply broken apart. Massive blocks of ice sit at odd angles, rotated and displaced from their original positions, frozen into new orientations like pieces of a jigsaw puzzle that someone scrambled and then flash froze before the pieces could settle. Connemara chaos is the most studied example. Blocks of ridged ice terrain appear to have drifted apart across a matrix of smoother, refrozen material, as though the surface briefly became liquid or slushy before solidifying again. The implication is inescapable. Something warm and dynamic exists beneath this frozen exterior, something capable of disrupting kilometers of solid ice from below. The mechanism driving this activity has a name: tidal heating, and understanding it requires understanding Europa's orbital relationship with Jupiter and with its neighbouring moons. Europa orbits Jupiter at a mean distance of approximately 671,000 kilometers, completing one full orbit every 3.5 Earth days. That orbital period is brisk by the standards of planetary satellites, but Europa does not orbit in isolation. It shares its gravitational neighbourhood with two other massive moons, Io and Ganymede, and the three of them are locked in a precise mathematical relationship called a Laplace resonance. For every single orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This ratio has been maintained for billions of years, enforced by the gravitational interactions between the three moons. The resonance has a critical consequence. It forces Europa's orbit into a slight ellipse rather than a perfect circle. Left to its own devices, Europa's orbit would gradually circularize through tidal interactions with Jupiter, but the periodic gravitational tugs from Io and Ganymede prevent this, maintaining a small but persistent orbital eccentricity that changes everything about the Moon's internal dynamics. An elliptical orbit means that Europa's distance from Jupiter varies slightly during each 3.5-day circuit. When the Moon swings closer to Jupiter, it experiences stronger gravitational pull. When it swings farther away, the pull weakens. This rhythmic variation in gravitational force flexes Europa's interior, stretching and compressing the Moon's body in a cycle that repeats with every orbit. The effect is comparable to repeatedly squeezing a rubber ball in your hand. The ball heats up from internal friction. Europa heats up the same way, except the squeezing force comes from the gravity of the largest planet in the solar system, and it has been operating continuously for roughly 4.5 billion years. The energy generated by this tidal flexing is not trivial. Scientists estimate that Europa's tidal heating budget falls in the range of approximately 100 billion watts, though the exact figure carries significant uncertainty. That is roughly 1/20th of the total heat flowing out of Earth's interior, generated in a body that is far smaller and has no internal radioactive heat sources comparable to Earth's. This energy flows outward from Europa's rocky interior, warming the base of the ice shell and maintaining a layer of liquid water that would otherwise freeze solid at Jupiter's distance from the Sun. Tidal heating is not theoretical. Its most dramatic confirmation exists on Io, the innermost of the 4 Galilean moons, where the same resonance mechanism operates with far greater intensity. Io orbits closer to Jupiter and experiences tidal forces so extreme that its entire interior is molten. The surface erupts continuously with volcanic activity so violent that lava fountains launch material hundreds of kilometers above the surface. Io is the most volcanically active body in the solar system, a world literally turned inside out by tidal forces. Europa experiences less tidal stress because it orbits farther from Jupiter, but the heating remains sufficient to prevent its ocean from freezing. Io shows what tidal heating does at full intensity. Europa shows what it does at a more moderate level, just enough to sustain liquid water beneath a frozen roof. The Galileo spacecraft provided the single most compelling piece of evidence for the ocean through its magnetometer instrument. As Europa orbited within Jupiter's enormously powerful magnetic field, the spacecraft detected a secondary magnetic field emanating from the Moon itself. This was not a permanent intrinsic field like Earth's, generated by a dynamo in a molten iron core. It was an induced field, created by the interaction between Jupiter's rotating magnetic field and a layer of electrically conductive material within Europa. The physics is straightforward. When a changing magnetic field encounters a conductor, it induces electrical currents in that conductor, and those currents generate their own magnetic field in response. Jupiter's magnetic field rotates with the planet, sweeping past Europa with a period of roughly 10 hours. If Europa contains a global layer of conductive fluid, that fluid would respond to the changing external field by generating an induced field with specific characteristics that depend on the conductor's depth, thickness, and conductivity. The induced field Galileo measured matched the predictions for a global ocean of salt water almost precisely. Fresh water is a poor conductor and would not produce a detectable signal. Solid ice conducts electricity poorly. But salt water, water containing dissolved ions like sodium, chloride, magnesium, and sulfate, conducts electricity well enough to generate exactly the kind of induced field Galileo observed. The magnetic evidence did not just suggest an ocean, it demanded one, and it demanded one that was salty. Subsequent analysis of the magnetic data, combined with models of Europa's interior structure, constrained the ocean's basic properties. The ocean appears to be global, wrapping around the entire moon beneath the ice shell rather than existing as isolated pockets or regional seas. Its depth may range from 60 to 150 kilometers, depending on the thickness of the ice shell above and the structure of the rocky interior below. This is not a shallow film of moisture trapped between ice and rock. It is a genuine ocean, deeper than any ocean trench on Earth, resting atop a rocky seafloor where tidal heating warms the interior from below. That rocky seafloor is not a minor detail. It is one of the most important features in the entire case for Europa as a potentially habitable world. On Earth, the most productive ecosystems that do not depend on sunlight exist at hydrothermal vents on the ocean floor. These vents form where seawater circulates through hot volcanic rock, emerging superheated and loaded with dissolved minerals like hydrogen sulfide, iron, and manganese. Chemosynthetic bacteria at these vents harvest chemical energy from the mineral-rich water, forming the base of food chains that support tube worms, shrimp, crabs, and fish in complete darkness, thousands of meters below the ocean surface. If Europa's ocean contacts warm rock heated by tidal flexing, similar hydrothermal systems could exist on its seafloor. Water circulating through cracks in the heated rock would dissolve minerals and carry chemical energy into the ocean. This would provide a source of energy for potential biological systems that is entirely independent of sunlight. Europa's ocean exists in perpetual darkness beneath kilometers of ice far from the sun. Photosynthesis is impossible, but chemosynthesis, the kind of biology that thrives at deep-sea vents on Earth, requires only water, rock, heat, and chemistry. Europa appears to have all four. The ingredients for life as scientists understand it require three fundamental components: liquid water to serve as a solvent for biochemical reactions, chemical energy to drive metabolism, and the right organic building blocks, carbon-containing molecules that can form the complex structures biology requires. Europa's case for habitability rests on evidence or strong inference for all three. The ocean provides the water. Tidal heating of the rocky interior could drive hydrothermal activity, providing chemical energy through water-rock reactions that produce hydrogen, methane, and other reduced compounds. And the surface of Europa, bombarded continuously by Jupiter's intense radiation, undergoes a process called radiolysis, where high-energy particles break apart water ice molecules and recombine the fragments into new compounds, including hydrogen peroxide, molecular oxygen, and various sulfur-bearing species. These radiation products, called oxidants, represent a second potential energy source. If geological processes cycle surface material downward into the ocean through cracks, convection, or other mechanisms, these oxidants could react with reduced compounds from hydrothermal vents, providing energy gradients that biology could exploit. This two-source energy model, combining hydrothermal chemistry from below with radiation chemistry from above, creates a theoretical energy budget for Europa's ocean that some scientists estimate could support a modest biosphere. Not a thriving ecosystem teeming with complex organisms, but perhaps microbial communities comparable in density to the least productive deep-sea environments on Earth. The comparison is humble, but humility is appropriate when discussing a world we have never directly sampled. This combination of properties places Europa in a scientific category distinct from any other body in the solar system. Mars is the traditional focus of astrobiology, and with good reason. Evidence strongly suggests that Mars once had liquid water on its surface billions of years ago, rivers, lakes, and possibly a shallow northern ocean. But that water is gone. The Martian surface today is a frozen desert, cold, irradiated, and dry. Any life that existed on Mars likely perished billions of years ago, and the search for Martian biosignatures is fundamentally a search for ancient fossils, chemical traces of organisms that lived and died before the planet lost its atmosphere and its water. Europa offers something categorically different. The ocean exists now. The tidal heating operates now. The chemistry is active now. If life ever arose in Europa's ocean, there is no obvious reason it would have gone extinct. The energy sources have been stable for billions of years. The ocean has been liquid for billions of years. The conditions that might support biology have persisted through nearly the entire history of the solar system. This makes Europa a target for detecting not ancient biosignatures from a dead world, but extant biology in a living ocean. The difference is profound. Finding fossil bacteria on Mars would be a monumental discovery. Finding living microbes on Europa would fundamentally transform our understanding of life in the universe. Enceladus, one of Saturn's small moons, presents the only serious rival to Europa as an astrobiological target. Enceladus also has a subsurface ocean, confirmed by the Cassini spacecraft through gravity measurements and the direct observation of water vapor geysers erupting from fractures at the moon's south pole. Cassini flew through those plumes and detected water, salts, silica nanoparticles suggesting hydrothermal activity, and simple organic molecules. The Enceladus data is in some ways more direct than anything we have from Europa, because the ocean material is literally shooting into space where a spacecraft can sample it. But Enceladus is tiny, approximately 504 kilometers in diameter, less than 1/7 the diameter of Europa. Its ocean may be regional rather than global, concentrated beneath the south polar region where the geysers originate. The total volume of liquid water is far smaller, and the long-term stability of its ocean is less certain. Enceladus may not have maintained liquid water for as long as Europa has, potentially reducing the time available for life to arise and develop. Europa's ocean is global, deep, ancient, and in contact with a rocky seafloor. These four properties together create the most compelling case for a habitable environment beyond Earth that planetary science has ever assembled. The scientific community has recognized this explicitly. NASA's Decadal Survey for Planetary Science, the document that sets priorities for the entire field, has repeatedly identified Europa as a top-tier target for future exploration. The surface features provide additional evidence of ongoing ocean-to-surface exchange. The reddish-brown material visible in chaos regions and along certain fractures has been analysed spectroscopically and appears to contain hydrated salts, possibly magnesium sulfate or sodium chloride, along with sulfur compounds. The exact composition remains debated, but the presence of salts on the surface is consistent with ocean-derived material that has been transported upward through the ice. If ocean water reaches the surface, the chemical connection between the hidden sea and the exposed ice is active, not ancient. The youth of Europa's surface reinforces this interpretation. Impact craters on Europa are remarkably scarce. Most rocky and icy bodies in the solar system are heavily cratered because their surfaces have accumulated impacts over billions of years. Europa's surface shows so few craters that scientists estimate its average age at between 40 million and 90 million years. This is extraordinarily young by geological standards. Something is continuously resurfacing the moon, erasing old craters and replacing them with fresh ice. The most likely explanation is that geological activity driven by the subsurface ocean is constantly recycling the surface, either through tectonic processes that crack and reorganize the ice, or through cryovolcanic eruptions that deposit new material on top of old terrain. A surface this young on a moon with confirmed tidal heating and a subsurface ocean suggests that Europa is not a static frozen world. It is geologically alive. Its interior is dynamic. Its ice shell is active. And its ocean is not a sealed tomb, but a system connected, at least intermittently, to the surface above and the rocky interior below. All of this evidence points toward a single, overwhelming conclusion. Europa's ocean is one of the most promising environments in the solar system for harboring life. The water is there. The energy is there. The chemistry appears to be there. The stability over billions of years is there. The scientific motivation for exploring this ocean is as strong as any motivation that has ever driven a space mission. But recognizing Europa's importance and actually exploring it are separated by a chasm so vast it dwarfs the physical distance between Earth and Jupiter. The ocean is real. The evidence is robust. The scientific case is overwhelming. And none of that matters if we cannot physically access what lies beneath the ice. Every mission concept aimed at Europa confronts a paradox that defines the entire endeavour. The destination that matters most, the liquid ocean, is the one place we cannot reach with any technology that currently exists. Getting a spacecraft to Europa's orbit requires years of patient interplanetary travel, but the techniques are well understood. Landing on the surface requires surviving a radiation environment that would kill an unshielded human in hours, but engineers know how to build radiation vaults. Operating instruments on the surface requires autonomous systems that can function without real-time commands from Earth. But autonomy is a mature field with decades of heritage from Mars rovers and deep space probes. None of those challenges are trivial, but they are all solvable with existing or near-term technology. The truly unsolved problem, the problem that may take decades of additional development to address, is what comes after landing. Descending through kilometers of ice, possibly tens of kilometers, into a pitch-black ocean with no communication link to the surface, no sunlight for power, no possibility of repair, and no margin for any error at any stage of a journey that could take years to complete. That is the challenge that separates Europa from every other destination humanity has ever attempted to explore. The scientific community understands this distinction clearly. Europa is not hard to reach because it is far away. It is hard to explore because the thing we want to study is buried beneath a barrier of ice whose thickness we do not precisely know, whose internal structure we have never measured directly, and whose properties at depth remain almost entirely theoretical. Distance is a logistical problem. Ice penetration is an engineering frontier. This reframing is essential for understanding everything that follows. The question in the title of this video is not really about travel time. A spacecraft could reach Europa in as few as 3 years with the right trajectory, or as many as 7 with a more conservative flight plan. Those numbers matter, but they are not the bottleneck. The bottleneck is access. The bottleneck is depth. The bottleneck is turning a confirmed ocean into a sampled ocean, and that transformation requires overcoming obstacles that no space mission has ever faced. What lies ahead in this story is not a tale of rockets and launch windows. It is a tale of ice, radiation, power, communication, contamination, and patience. The next chapter examines what happens when a spacecraft arrives at Jupiter and discovers that the hardest part of the journey has not even begun. The distance between Earth and Jupiter is not a fixed number. It changes constantly as both planets trace their separate elliptical paths around the Sun at different speeds and different distances. Earth completes its orbit in 365 days. Jupiter takes nearly 12 Earth years to complete one circuit. The result is a gravitational dance where the two planets swing closer together and then drift apart on a cycle of approximately 399 days. At their nearest approach, called opposition, Jupiter lies approximately 588 million kilometers from Earth. At their farthest separation, when the Sun sits directly between them, The gap stretches to nearly 968 million kilometers. These distances are so large that even light, the fastest thing in the universe, requires significant time to cross them. A photon leaving Earth at opposition reaches Jupiter in approximately 33 minutes. At maximum separation, the same journey takes roughly 53 minutes. This light travel delay is not an academic curiosity. It fundamentally constrains how missions to the Jupiter system operate. When a spacecraft orbiting Europa sends a signal back to Earth, mission controllers will not receive it for at least half an hour. Their response will take another half hour to arrive. Every command, every correction, every instruction crosses a communication gap measured in hours, not seconds. Real-time piloting is impossible. Everything a spacecraft does at Jupiter must be either pre-programmed before the maneuver begins or decided autonomously by onboard computers. But spacecraft do not travel at the speed of light. They travel at speeds dictated by the rockets that launch them and the orbital mechanics that guide them. And they do not fly in straight lines. A spacecraft bound for Jupiter follows a curved trajectory through the solar system, a path shaped by the gravitational fields of every massive body it encounters along the way. The most efficient routes to Jupiter exploit a technique called gravity assist, where a spacecraft flies close to a planet and uses that planet's gravity and orbital motion to gain speed without burning any fuel. This free acceleration comes at a cost. It requires precise timing and adds years to the journey as the spacecraft loops through the inner solar system before heading outward. The history of Jupiter-bound missions illustrates the range of possible travel times. Pioneer 10, launched in March of 1972, reached Jupiter in approximately 21 months using a direct trajectory with no gravity assists. It was the first spacecraft to cross the asteroid belt and the first to encounter Jupiter up close. Pioneer 11 followed a year later on a similar timeline. Both missions were flyby encounters. They screamed past Jupiter at tremendous speed, collected data during brief windows of closest approach, and continued onward into the outer solar system without slowing down. The Voyager missions, launched in 1977, reached Jupiter in roughly 18 months each, again on flyby trajectories that used Jupiter's gravity to redirect them towards Saturn and beyond. These missions demonstrated that fast transit to Jupiter was achievable with existing rocket technology, but only if you had no intention of stopping. Flying past a planet at 12 kilometers per second gives you hours of close observation. Entering orbit requires burning engines to slow down, which demands carrying fuel, which adds mass, which requires a bigger rocket, which limits the scientific payload you can bring. The Galileo spacecraft confronted this problem directly. Launched in October of 1989, Galileo was designed to enter Jupiter orbit and study the system for years rather than hours. But the spacecraft was too heavy to reach Jupiter on a direct trajectory with the rockets available. Instead, mission planners designed an elaborate gravity assist sequence. Galileo flew past Venus once and Earth twice, using each encounter to gain speed incrementally. The total flight path covered approximately 4.6 billion kilometers, a distance roughly 5 times the straight-line separation between Earth and Jupiter at opposition. The journey took 6 years. Galileo did not arrive at Jupiter until December of 1995. 6 years. That number represents a realistic baseline for any mission designed to orbit Jupiter rather than simply fly past it. The Juno spacecraft, launched in August of 2011, reached Jupiter in July of 2016 after a 5-year transit that included 1 Earth gravity assist. Juno is a polar orbiter studying Jupiter itself rather than its moons, but its travel time reflects the same fundamental constraints. Getting to Jupiter fast enough to be useful but slow enough to enter orbit requires multi-year transits regardless of the specific trajectory chosen. The Europa Clipper mission, which launched in October of 2024, follows a trajectory that includes gravity assists from both Mars and Earth. Its expected arrival at Jupiter is approximately 2030, a transit time of roughly 6 years. This timeline accounts for the spacecraft's mass, the energy needed to enter Jupiter orbit, and the geometry of planetary positions during the launch window. A future Europa lander mission would face similar constraints. Depending on its mass, propulsion system, and the planetary alignment at launch, transit times of 5 to 8 years are realistic estimates. Could we get there faster? In principle, yes. More powerful rockets or advanced propulsion systems could shorten the journey. Nuclear thermal propulsion, which heats hydrogen propellant using a nuclear reactor and expels it at higher velocities than chemical rockets can achieve, has been studied since the 1960s and could potentially reduce Jupiter transit times to 3 or 4 years for appropriately sized payloads. Nuclear electric propulsion, which uses a reactor to power ion engines providing continuous low thrust over long periods, offers another pathway to faster or more efficient transit. But neither technology has been demonstrated on an interplanetary mission. Both require significant development before they could be trusted with a multi-billion-dollar payload bound for the outer solar system. Solar electric propulsion faces a fundamental limitation beyond Mars orbit. The intensity of sunlight decreases with the square of the distance from the Sun. At Jupiter's average distance of 5.2 astronomical units, solar panels receive only about 3.7% of the energy they would collect in Earth orbit. Powering ion engines with solar electricity at Jupiter requires enormous solar arrays, and even then the available thrust is modest. Europa Clipper carries solar panels spanning roughly 30 meters from tip to tip, the largest ever sent to the outer solar system. And even these massive arrays will generate only about 700 watts of usable power at Jupiter, enough to run the spacecraft's instruments and communication systems, but not enough to provide the surplus power that advanced propulsion would demand. The honest summary is this: getting a spacecraft to Europa takes between 3 and 8 years depending on the trajectory, propulsion system, and mission mass. This is a long time by human standards, but a solved problem by engineering standards. We know how to build spacecraft that survive multi-year interplanetary cruises. Voyager 1 and 2 have been operating for nearly 5 decades. The challenge of reaching Jupiter's neighborhood is real but understood. The techniques are proven, the timelines are predictable. But here is where the conversation must pivot sharply. Because reaching Jupiter's neighborhood is not the same as reaching Europa's surface. And reaching Europa's surface is not the same as reaching Europa's ocean. The word reaching hides 3 completely different engineering challenges of escalating difficulty, and the transition from the first to the second involves encountering an environmental hazard so severe that it redefines what survival means for a spacecraft. Jupiter possesses the most powerful planetary magnetic field in the solar system, generated by currents of metallic hydrogen flowing deep within the planet's interior. Jupiter's magnetosphere extends millions of kilometers into space, engulfing all 4 Galilean moons and stretching so far in the direction away from the Sun that its magnetotail reaches nearly to Saturn's orbit. The magnetic field at Jupiter's cloud tops measures approximately 4.2 Gauss, roughly 10 to 20 times stronger than the magnetic field at Earth's surface, while its overall magnetic moment is approximately 20,000 times larger. This immense magnetic field acts as a trap for charged particles. Protons and electrons from the solar wind are captured by the field and accelerated to tremendous energies as they spiral along magnetic field lines. Additional particles come from Io, whose volcanic eruptions spew roughly 1 ton of sulfur dioxide per second into space. This material becomes ionized by solar radiation, and Jupiter's magnetic field sweeps it up, creating a dense plasma torus encircling Jupiter along Io's orbital path. The trapped particles bounce back and forth between Jupiter's magnetic poles, gaining energy with each interaction, building up a radiation environment of extraordinary intensity. Europa orbits at approximately 9.4 Jupiter radii from the planet's center, placing it deep within the most intense region of Jupiter's radiation belts. The radiation dose on Europa's surface has been estimated at approximately 540 rem per day. To put this number in context, that means something. The annual radiation exposure limit for a trained radiation worker on Earth is 5 rem. A lethal dose for a human, one that would cause death within weeks even with medical treatment, is approximately 400 rem delivered over a short period. Standing unshielded on Europa's surface, A human being would absorb a lethal dose in less than 24 hours. Within 2 days, the accumulated dose would be so extreme that no medical intervention could prevent death. Spacecraft electronics are more resilient than human tissue, but they are far from immune. High-energy electrons, the dominant radiation threat in Jupiter's magnetosphere, penetrate spacecraft structures and deposit energy in semiconductor materials. This energy creates electron-hole pairs in transistors, gradually shifting voltage thresholds and degrading circuit performance. Individual high-energy particle strikes can flip bits in computer memory, corrupt stored data, or trigger false signals in sensors. Cumulative radiation exposure degrades solar cell efficiency, darkens optical elements in cameras and spectrometers, and weakens structural materials through atomic displacement damage. The Galileo spacecraft experienced these effects firsthand during its 8 years in Jupiter orbit. Despite radiation-hardened electronics designed to withstand the environment, several instruments degraded over the course of the mission. The spacecraft's high-gain antenna failed to deploy fully, possibly due to mechanisms affected by thermal cycling and radiation. The onboard tape recorder, critical for storing data between communication sessions with Earth, experienced malfunctions that required creative workarounds by the mission team. By the end of the mission, cumulative radiation damage had significantly reduced the spacecraft's capabilities. Juno addresses this problem through orbital design. Rather than orbiting close to Jupiter continuously, Juno follows a highly elliptical polar orbit that brings it close to the planet for brief periods of intense data collection before retreating to distances far beyond the worst radiation zones. Each close approach, called a perijove, lasts only a few hours. The spacecraft spends most of each 53-day orbit far from Jupiter, where radiation levels are comparatively benign. Even with this protective strategy, Juno's most sensitive electronics are housed inside a titanium radiation vault with walls approximately 1 centimeter thick, weighing roughly 180 kilograms. This vault reduces the radiation dose reaching the electronics by approximately 800 times compared to unshielded exposure. A lander sitting on Europa's surface cannot employ Juno's strategy. There is no retreating to a safer distance. From the moment the landing legs touch ice, the spacecraft is immersed in the radiation environment continuously. Every hour on the surface accumulates dose. Every day degrades performance. The clock is running from the instant of touchdown, and it does not stop until the mission ends. NASA's Jet Propulsion Laboratory conducted extensive studies of a Europa lander concept and concluded that meaningful surface operations would be limited to approximately 20 to 30 days before cumulative radiation damage rendered critical systems unreliable. Some analyses are more conservative, suggesting that high-confidence science operations might be achievable for only 15 to 20 days. The exact number depends on the shielding mass budget, the radiation tolerance of specific electronic components, and the acceptable probability of system failure during the mission. This time constraint imposes a discipline on mission design that has no parallel in the history of planetary exploration. The Mars rovers Spirit and Opportunity were designed for 90-day missions and operated for years. Curiosity has been exploring Gale Crater since 2012, with no foreseeable end to its mission. The Cassini spacecraft orbited Saturn for 13 years. These missions had the luxury of time. They could afford instrument calibration periods, software updates, course corrections, and the kind of iterative science where early observations inform later investigations. A Europa lander has none of this luxury. 20 days means 20 days. Every instrument must work correctly from the moment it powers on. Every experiment must be designed to produce definitive results within the operational window. Every byte of data must be transmitted to the orbiting relay before radiation claims the communication system. There is no second attempt. There is no extended mission. There is no recovery from a failed deployment or a corrupted dataset. The radiation environment converts every operational minute into a non-renewable resource that must be spent with absolute precision. The radiation also affects the scientific integrity of surface samples. Jupiter's magnetospheric particles have been bombarding Europa's ice for billions of years, processing the top layer of the surface through a phenomenon called radiolysis. High-energy electrons and ions break apart water molecules, recombine the fragments into new compounds, and gradually transform the upper meter or so of ice into a chemically altered layer containing hydrogen peroxide, molecular oxygen, sulfuric acid, and various sulfur polymers. This radiation-processed veneer is scientifically interesting in its own right, but it presents a serious complication for anyone searching for biosignatures that may have originated in the ocean below. If ocean-derived material reaches Europa's surface through cracks or geological cycling, any biological molecules it once contained would be exposed to this radiation bombardment. Complex organic compounds are fragile. High-energy particles can shatter carbon chains, break peptide bonds, and decompose amino acids into simpler fragments. The very radiation that creates interesting surface chemistry also destroys the biological signatures that a lander would most want to detect. A surface sample collected from the top few centimeters of ice would be dominated by radiation products rather than pristine ocean chemistry. This means a lander searching for biosignatures must dig, not deep by the standards of ice penetration, but deep enough to get below the radiation-processed layer. Estimates suggest that digging to a depth of approximately 10 to 20 centimeters would access material that has been less heavily processed. Reaching a depth of 1 to 2 meters would likely encounter ice that has been substantially shielded from surface radiation. But even shallow digging on Europa's surface requires hardware that consumes mass, power, and time, all of which are severely constrained by the radiation-imposed operational window. The radiation environment also constrains where a spacecraft can land. Europa's surface does not receive radiation uniformly. The trailing hemisphere, the side facing away from the Moon's direction of orbital motion, receives somewhat less radiation than the leading hemisphere due to the geometry of particle flows within Jupiter's magnetosphere. Energetic electrons trapped in the magnetosphere tend to overtake Europa in its orbit, preferentially bombarding the trailing hemisphere from behind. But the dose difference between hemispheres is modest, perhaps a factor of 2, and does not fundamentally change the survival timeline for a lander. It does, however, slightly favour landing sites on the trailing hemisphere when all other factors are equal. The latitude of the landing site also matters. Jupiter's radiation belts are concentrated near the magnetic equator, which roughly aligns with Europa's orbital plane. Regions near Europa's poles receive somewhat less radiation than equatorial zones, but the dose reduction at polar latitudes is modest and must be weighed against other considerations like surface terrain, communication geometry, and scientific interest. The most geologically active and scientifically compelling regions of Europa's surface, including the chaos terrain and the youngest fracture systems, are not exclusively concentrated at the poles. Communication from Europa's surface introduces an additional layer of difficulty that compounds the radiation problem. A lander on the surface cannot transmit directly to Earth with the kind of high-bandwidth link needed to return detailed scientific data. The power requirements for a direct-to-Earth transmission from Jupiter's distance would exceed what any reasonably sized lander could generate. Instead, the lander must relay its data through an orbiting spacecraft that can store the information, amplify the signal, and transmit it to Earth using a high-gain antenna. This relay architecture creates a dependency chain. The orbiting relay spacecraft must survive long enough in Jupiter's radiation environment to receive all of the lander's data and forward it to Earth. If the relay fails before the lander completes its science operations, the data is lost. If the relay's orbit carries it out of communication range at a critical moment, the lander must store data and wait for the next overpass. Every gap in relay coverage is time that the lander spends on the surface accumulating radiation dose without transmitting results. The one-way light travel time between Europa and Earth adds a delay of 33 to 53 minutes depending on orbital geometry. Round-trip communication requires over an hour at minimum. During that hour, the lander must operate autonomously, executing pre-programmed sequences or making decisions through onboard software without human guidance. If something goes wrong, if a drill jams, If a sample container fails to seal, if a sensor produces anomalous readings, the spacecraft must diagnose the problem and implement a solution before the operations team on Earth even learns that something has happened. This autonomy requirement is not new. Mars rovers have operated with similar communication delays for decades. But Mars rovers have the luxury of stopping, assessing, and waiting for instructions when they encounter unexpected situations. A Europa lander operating under a 20-day radiation clock cannot afford to pause. Every hour spent waiting for guidance from Earth is an hour closer to system degradation. The operational tempo must be relentless, and the onboard decision-making software must be robust enough to handle contingencies that engineers on Earth might need days to resolve. All of these factors, the multi-year transit, the radiation exposure timeline, the communication delays, the autonomous operations requirements, the sample contamination challenges, converge on a single stark realization that reframes the entire Europa exploration narrative. The journey to Europa is measured in years, survival on the surface is measured in days, and the gap between arriving at Europa and accessing its ocean is not merely a technical step. It is a transition from the realm of proven engineering into territory where no existing technology is adequate. Consider what a Europa surface mission actually accomplishes in the context of ocean exploration. A lander that operates for 20 days on the surface, digs a few shallow trenches, and analyzes samples from the upper meter of ice is performing vitally important science. It is characterizing the surface environment, testing for biosignatures in radiation process material, measuring the local radiation field, and providing ground truth for orbital observations. But it is not accessing the ocean. It is not even close to the ocean. The ocean lies kilometers below, separated from the lander by a barrier of ice that the surface mission cannot penetrate. The surface mission is a prerequisite, not a destination. It gathers the data needed to design the next mission, the one that actually attempts to reach the water. What is the ice composition at the landing site? What is the thermal gradient near the surface? Are there signs of recent geological activity that might indicate thinner ice nearby? What is the mechanical strength of the surface ice? Each of these measurements informs the engineering of an ice-penetrating probe, but none of them brings the probe itself any closer to reality. This is the fundamental tension at the heart of Europa exploration. The scientific prize, the ocean, sits behind a barrier that cannot be breached by any mission currently in development. The missions we can build today, orbiters and landers, are reconnaissance tools. They map the battlefield. They identify the weaknesses in the ice. They test whether biosignatures survive near the surface. They build the knowledge base that future engineers will need. But the actual penetration of the ice, the moment a human-built instrument first touches liquid water on another world, lies beyond the horizon of current capability. The radiation environment makes this gap even more painful because it limits how much preparatory work can be accomplished at the surface. A lander with years of operational life could conduct extensive surveys, drill multiple test holes, characterize ice properties at various depths, and gradually build the dataset needed for a subsurface mission design. A lander with 20 days cannot do any of this at the depth required. It can scratch the surface, collect what it can, transmit what it finds, and die. The radiation ensures that surface characterization will be brief, incomplete, and unrepeatable without another multi-billion-dollar mission. The next chapter confronts the challenge that lies beyond the surface directly. Not the journey to Europa, not the survival on its ice, but the descent through that ice into darkness, into silence, into an ocean that has never been touched by anything from beyond its frozen ceiling. This is where the engineering moves from the difficult to the unprecedented, where every proposed solution exists only on paper, in laboratories, or in the imaginations of engineers who understand that what they are attempting has never been done and may not be achievable for decades. The ice stands between every instrument we can build and the ocean those instruments need to reach, and it is not going to make this easy. On the Antarctic ice sheet, at a Russian research station called Vostok, a team of engineers spent decades drilling a single borehole through glacial ice. The project began in 1970 and did not reach its target until February of 2012, when the drill bit finally punctured through 3,769 meters of ice and tapped into a subglacial lake that had been sealed from the outside world for an estimated 15 million years. The achievement was celebrated as one of the most ambitious drilling projects in scientific history. It required continuous resupply by aircraft. It employed rotating teams of specialists living in pressurized shelters on the ice. It consumed diesel fuel for heating, electricity for drilling, and antifreeze fluids to keep the borehole from collapsing. When problems arose, and they arose frequently, engineers could diagnose the issue, fabricate replacement parts, and try again. The drill bit was approximately 13 centimeters wide. The borehole took 42 years to complete. Europa's ice shell may be 3 to 10 times thicker than the Vostok ice sheet. The surface temperature hovers around minus 160 degrees Celsius, roughly 110 degrees colder than the coldest temperature ever recorded at Vostok Station. At these temperatures, water ice behaves less like the slippery substance you find in a freezer and more like granite. Its compressive strength increases dramatically. Its thermal conductivity changes. The energy required to warm it to the melting point is vastly greater than for terrestrial glacial ice that sits only a few tens of degrees below freezing. There is no atmosphere on Europa to provide even minimal thermal insulation. There is no resupply chain. There are no human engineers standing by with replacement parts and creative workarounds. There is no electricity grid, no fuel depot, no workshop, and every proposed method for penetrating this ice must operate entirely on its own, from the first centimetre to the last kilometre, without any intervention from Earth. The most widely studied approach for penetrating Europa's ice shell is a class of device called a cryobot. The concept descends from an idea first proposed in the 1960s for exploring Earth's polar ice caps and later refined by NASA engineers studying planetary exploration scenarios. The basic principle is elegant in its simplicity. A cylindrical probe, typically envisioned as roughly 20 to 30 centimeters in diameter and 1 to 2 meters in length, generates heat at its leading tip. That heat melts the ice directly in front of the probe. Gravity pulls the probe downward into the melt channel. The water displaced by the probe flows around its body to the space above, where it refreezes as the surrounding ice absorbs the thermal energy. The probe descends continuously, centimeter by centimeter, leaving a column of refrozen ice behind it that seals the channel almost as quickly as it opens. The beauty of a melt probe lies in what it avoids. There are no rotating drill bits that wear out against rock-hard ice. There are no cuttings to extract from the borehole. There is no need to maintain an open shaft behind the probe, because the ice refreezes naturally. The mechanical simplicity is extraordinary. In principle, a melt probe has almost no moving parts. It is just a heated cylinder sinking through ice under its own weight, letting physics do the heavy lifting. Terrestrial prototypes have demonstrated the concept in glacial ice on Earth. NASA's Jet Propulsion Laboratory, the German Aerospace Center, and several university research groups have built and tested small-scale cryobots in laboratory ice blocks and in glaciers in Alaska, Greenland, and Antarctica. The physics works. Ice melts. The probe descends. Data confirms the basic feasibility of the approach. But the gap between a laboratory prototype melting through a few meters of temperate glacial ice and a flight-qualified probe descending through 10 or 20 kilometers of cryogenic extraterrestrial ice is not a gap, it is a canyon. Every aspect of the concept that functions smoothly in controlled terrestrial conditions encounters severe complications when scaled to Europa's environment. The simplicity that makes the cryobot concept attractive on paper conceals engineering challenges so demanding that no research group in the world has solved them. The first and most fundamental challenge is power. Melting ice requires thermal energy, and the amount of energy needed scales directly with the temperature difference between the ice and its melting point, the cross-sectional area of the probe, and the desired descent rate. At Europa's surface temperatures, the ice must be heated through a temperature differential of approximately 160 degrees Celsius before it even begins to approach the melting point. Then, additional energy must overcome the latent heat of fusion, the energy needed to break the molecular bonds holding the ice crystal structure together and convert solid ice to liquid water. This latent heat amounts to approximately 334 kilojoules per kilogram of ice, a substantial energy investment that cannot be reduced by any engineering trick. For a probe 20 centimeters in diameter descending at a rate of roughly 1 meter per hour, the continuous thermal power requirement falls in the range of 5 to 10 kilowatts. This number is not speculative. It emerges directly from thermodynamic calculations that have been verified against terrestrial melt probe experiments. 5 to 10 kilowatts of heat, delivered continuously, without interruption, for the entire duration of the descent. How long is that descent? The answer depends on the thickness of the ice, which remains one of the great unknowns of Europa science. Models based on thermal equilibrium calculations, surface feature analysis, and tidal heating estimates produce a wide range of predictions. At the optimistic end, some models suggest the ice could be as thin as 2 to 5 kilometers in certain regions, particularly near chaos terrain, where the shell may have been recently disrupted from below. At the conservative end, models incorporating solid-state convection within the ice shell predict thicknesses of 15 to 30 kilometers or more. The difference is not academic. It determines whether the descent takes months or years. At 1 meter per hour through a 5-kilometer shell, the descent takes approximately 5,000 hours, or roughly 208 days. Through a 15-kilometer shell, the journey extends to approximately 625 days. Through a 30-kilometer shell, the probe would need to melt continuously for nearly 3.5 years. Throughout every hour of this descent, the power source must deliver its full thermal output without degradation, without fuel consumption, and without maintenance. Any interruption in power, even for a few hours, allows the meltwater around the probe to refreeze. Once the ice resolidifies against the probe's body, the device is trapped. Restarting the heating system might free it, or the refrozen ice might grip the probe so tightly that the available thermal output cannot overcome the bond. A power interruption deep within Europa's ice shell could mean permanent entombment. The only realistic power source for this application is nuclear. Solar energy is irrelevant beneath an ice shell that blocks all sunlight. Chemical batteries lack the energy density to sustain kilowatt-level output for months or years. Chemical fuel cells face the same limitation. Radioisotope thermoelectric generators, the plutonium-238 powered devices that have served deep space missions since the 1960s, generate electricity from the heat of natural radioactive decay. They are extraordinarily reliable. The Voyager spacecraft still operate on RTG power nearly 5 decades after launch. But standard RTGs produce relatively modest electrical power, typically a few hundred watts at the beginning of a mission, declining gradually as the plutonium decays. Converting RTG heat directly to thermal output for melting is more efficient than converting to electricity first. But even the most optimistic RTG configurations struggle to reach the multi-kilowatt thermal levels needed for reasonable descent rates. A dedicated nuclear fission reactor offers a path to higher power levels. NASA and the Department of Energy demonstrated a compact fission reactor called Kilopower in ground tests between 2017 and 2018. The system used a uranium-235 core, roughly the size of a paper towel roll, and produced approximately 1 kilowatt of electricity, with several kilowatts of thermal energy available as waste heat. Scaling this concept to the 5 to 10 kilowatt thermal range needed for ice penetration is theoretically feasible, but has never been demonstrated in any operational environment, let alone inside a cylindrical probe descending through extraterrestrial ice. Miniaturizing a fission reactor to fit within a probe body 20 to 30 centimeters in diameter introduces fierce engineering constraints. The reactor core, its shielding, its heat transfer systems, its control mechanisms, and its structural support must all fit within a volume roughly equivalent to a large suitcase while operating safely and reliably for years. The shielding is particularly problematic. Fission reactions produce neutron and gamma radiation that would damage the probe's instruments and electronics if not adequately blocked. But shielding adds mass, and mass determines whether the probe is heavy enough to descend through the ice under gravity alone or whether it stalls against the frictional resistance of the surrounding melt channel. Every kilogram of shielding is a kilogram that cannot be allocated to scientific instruments, communication hardware, or structural reinforcement. The second major engineering obstacle is communication. As the probe descends, the growing column of ice above it progressively blocks electromagnetic signals. Radio waves attenuate severely in ice, particularly at the frequencies commonly used for spacecraft communication. The attenuation depends on the ice temperature, its purity, and the signal frequency. But even under optimistic assumptions, conventional radio communication between a submerged probe and a surface relay becomes essentially impossible beyond a depth of a few hundred meters. At 1 kilometer depth, the signal strength would be so far below the noise floor that no practical receiver could extract it. At 5 or 10 kilometers, the ice might as well be a solid wall of lead for radio purposes. The most commonly proposed solution is a physical tether. A thin fiber optic cable or electrical wire, spooled within the probe's body, would unspool behind the probe as it descends, maintaining a direct physical connection to a relay station on the surface. Data would travel up the tether as optical or electrical signals, reach the surface relay, and then be transmitted by radio to an orbiting spacecraft for forwarding to Earth. Fiber optic tethers offer enormous bandwidth, potentially gigabits per second, more than enough to transmit high-resolution images, spectra, and environmental measurements in real time. The concept sounds straightforward, the execution is anything but. A tether spanning 10 to 20 kilometers must be thin enough to coil inside the probe body without consuming an unacceptable fraction of the interior volume. It must be strong enough to support its own weight over that length without snapping. It must be flexible enough to navigate any lateral deviations in the probe's descent path caused by density variations, embedded debris, or convective motion within the ice. And it must survive the thermal and mechanical stresses of being embedded in refreezing ice that exerts inward pressure as it solidifies around the cable. The refreezing problem is particularly insidious. As the probe descends and melt water flows upward around its body, that water refreezes relatively quickly once it moves away from the heated zone. The refreezing ice grips the tether and applies compressive stress. Over kilometers of depth, the cumulative force on the tether can be enormous. Any imperfection in the cable, a microscopic nick, a localized stress concentration, a point where the ice refroze unevenly, could become the site of a break. A single break anywhere along the tether's length severs the communication link permanently. The probe continues descending in silence, collecting data it can never transmit. Alternative communication concepts have been proposed, each with significant limitations. Acoustic signaling through the ice uses sound waves rather than electromagnetic waves to carry data. Ice is a reasonably good conductor of sound, and acoustic signals can propagate through kilometers of solid ice with detectable amplitude. But the achievable data rates are extremely low, perhaps a few bits per second under realistic conditions, compared to the megabits or gigabits achievable through fiber optics. Transmitting a single high-resolution image at acoustic data rates could take days. Transmitting the comprehensive dataset a subsurface mission would generate could take years, assuming the acoustic link remains stable over that duration. Another concept involves deploying relay nodes at intervals within the ice as the probe descends. Each node would be a small communication station embedded in the refreezing ice behind the probe, receiving signals from the node below it and forwarding them upward to the node above. This daisy chain architecture distributes the communication challenge across multiple shorter links rather than a single long one, but it adds mass, complexity, and dozens of additional failure points to the system. Each relay node must function independently for years in an environment where it is slowly being compressed by refreezing ice. and where temperatures vary from -160 degrees near the surface to approximately 0 degrees, near the ocean interface. The third critical challenge involves the ice shell itself as a dynamic geological structure rather than a passive barrier. Europa's ice is not a uniform block of frozen water. It is a complex, layered, and possibly convecting medium whose internal properties vary with depth in ways that are largely theoretical. Near the surface, the ice is extremely cold and mechanically rigid. This upper layer, called the conductive lid, transfers heat primarily through thermal conduction. Its thickness depends on the total heat flux from below and the surface temperature, but estimates range from roughly 2 to 10 kilometers. Within this conductive layer, the ice behaves relatively predictably for a melt probe. It is cold, hard, and stationary. Below the conductive lid, if the ice shell is thick enough, the situation changes dramatically. Warmer ice at depth becomes soft enough to flow plastically, and if the temperature gradient is sufficient, the ice begins to convect. Warm ice rises, cool ice sinks. Slow-motion circulation cells develop, analogous to the convection patterns in Earth's mantle, but operating in ice rather than rock, and on timescales of thousands to millions of years. This convecting layer, if it exists, could extend from below the conductive lid all the way down to the ocean interface. A probe descending through convecting ice faces a problem that no terrestrial test can fully replicate. The ice is not stationary, it is moving. A region of warm upwelling ice could carry the probe laterally or even upward, counteracting the downward descent driven by gravity and melting. If the convective velocity in an upwelling zone approaches or exceeds the probe's melt rate, the probe could stall, carried along with the rising ice like a leaf caught in a slow updraft. Navigating through convecting ice might require the probe to sense its environment, detect convective flows, and actively steer to avoid upwelling zones. This demands sensors, processing capability, and mechanical steering systems that add mass and complexity to a design already constrained by the need to fit everything inside a narrow cylinder. The ice may also contain impurities that complicate the melting process. Salt inclusions concentrated at grain boundaries, pockets of liquid brine that remain unfrozen even at low temperatures due to their high salinity, and layers of dust or debris accumulated from meteorite impacts over billions of years could all create zones where the thermal and mechanical properties of the ice change abruptly. A probe calibrated for pure water ice might encounter a brine pocket and experience a sudden decrease in resistance, dropping faster than expected. Or it might hit a layer of silicate debris and encounter material that does not melt at all, requiring mechanical drilling capability that a pure melt probe does not possess. This possibility has led some researchers to propose hybrid systems that combine thermal melting with mechanical cutting. A rotating drill head at the probe's tip could break through rocky inclusions or dense debris layers that resist thermal melting alone, while the heating system handles the bulk ice. But adding a mechanical drill introduces exactly the moving parts and wear surfaces that the melt probe concept was designed to avoid. Drill bits wear out, motors consume power, cuttings must be managed. The hybrid approach solves one problem by reintroducing others. The fourth challenge operates at the boundary between engineering and ethics. Planetary protection, the set of international protocols designed to prevent the contamination of potentially habitable extraterrestrial environments with terrestrial biology, imposes requirements on a Europa subsurface mission that are among the most stringent ever applied to any spacecraft. The Committee on Space Research, known as COSPAR, classifies missions based on the type of body they visit and the nature of the encounter. A mission that contacts the surface of a world with potential for harboring life falls under Category 4 restrictions, requiring demonstrated sterilization to levels that minimize the probability of introducing viable terrestrial organisms. A mission that directly contacts a subsurface liquid water environment on such a world faces even more demanding requirements under Category 4 subcategories that some mission planners informally describe as beyond anything previously attempted. The core concern is straightforward. Earth teems with extremophilic microorganisms, bacteria, and archaea that thrive in conditions once thought incompatible with life. Organisms have been found surviving in the cores of nuclear reactors, in the superheated water of deep-sea hydrothermal vents, in the frigid interiors of Antarctic ice sheets, in the desiccated soils of the Atacama Desert, and in the vacuum of space itself aboard the exterior surfaces of the International Space Station. Some of these organisms form spores that can survive radiation, extreme cold, and vacuum for years or decades, reactivating when conditions improve. If even a single viable spore hitchhikes on a probe that descends through Europa's ice and enters the ocean, the consequences could be profound. In the worst case, the organism could find Europa's ocean habitable, establish a population, and irreversibly contaminate an ecosystem that had been biologically isolated for 4.5 billion years. This would not just compromise future scientific investigations, it would destroy the very thing the mission was designed to study. A contaminated Europa ocean would be scientifically useless for astrobiology, because any organism found there could never be definitively attributed to indigenous biology rather than terrestrial contamination. The contamination concern also runs in reverse, creating what might be called the false positive problem. If a probe reaches the ocean and detects something that resembles biological activity, molecular signatures consistent with life, microscopic structures resembling cells, chemical gradients suggesting metabolism, scientists must be able to demonstrate with high confidence that the detection reflects indigenous European biology rather than terrestrial organisms that survived the sterilization process. If the probe was not perfectly clean, the discovery could be dismissed as contamination. A discovery that could reshape our understanding of life itself could be undermined by a single surviving spore. Sterilizing a spacecraft intended for Europa's ocean requires eliminating viable organisms from every surface, every crevice, every internal cavity, and every material layer of the probe and its supporting hardware. Standard sterilization techniques include dry heat treatment, exposure to hydrogen peroxide vapor, and gamma radiation. Each method has limitations. Dry heat can damage sensitive electronics and degrade certain materials. Chemical sterilants may not penetrate sealed volumes or complex mechanical assemblies. Radiation sterilization requires doses high enough to kill the most resistant spores, which can also damage semiconductor materials and optical elements. The sterilization challenge is compounded by the nuclear power source. A fission reactor contains uranium fuel, neutron moderators, control elements, and shielding materials that cannot easily be subjected to high-temperature baking or chemical treatment without risk of damage. The reactor must be integrated with the probe after sterilization of the other components, introducing a potential recontamination pathway that must be managed through cleanroom procedures and verified through biological assays. Verification is itself a challenge. How do you confirm that a complex piece of hardware is sterile? You cannot swab every surface of a sealed probe. You cannot culture samples from the interior of a nuclear reactor core. Standard bioburden assays test representative surfaces and extrapolate to the whole device, but extrapolation carries uncertainty. The required confidence level for a Europa ocean mission, a probability of contamination below approximately 1 in 10,000 over the mission lifetime, demands verification methods that push the limits of current microbiology. The fifth challenge awaits at the end of the descent. If a probe successfully melts through the entire ice shell and emerges into liquid water, it enters an environment whose properties are almost entirely unknown. The ocean pressure at the base of even a thin 5-kilometer ice shell would be approximately 500 atmospheres, comparable to the pressure at the bottom of Earth's deepest ocean trenches. If the ice is 20 or 30 kilometers thick, the pressure at the ice-ocean interface could exceed 1,500 atmospheres, far beyond the operating range of most scientific instruments designed for space missions. The ocean has never been touched by sunlight. No photon has penetrated that ice shell in the entire history of the solar system. Any imaging, navigation, or environmental sensing must rely on artificial light sources or non-optical methods like sonar. The probe would need to orient itself, avoid obstacles, and navigate towards scientifically interesting features like potential hydrothermal vents on the seafloor, all without any prior mapping data, and no external reference points and no real-time guidance from Earth. The ocean's chemical composition is constrained by models but not measured directly. If it contains high concentrations of magnesium sulfate, the water would be dense and viscous compared to Earth's oceans. If sodium chloride dominates, the properties would be more Earth-like but still alien. Sulfuric acid or other corrosive compounds could attack the probe's exterior surfaces and degrade instruments over time. Designing hardware that functions reliably in an ocean whose chemistry is known only through inference and modeling requires conservative engineering margins that add mass and reduce scientific capability. Even if every engineering obstacle is solved, even if the probe survives the descent and enters the ocean intact, a question remains that is rarely discussed in popular accounts of Europa exploration. What does the probe actually do once it gets there? The cryobot, by its nature, is a tunneling machine. It is designed to go down. Its shape, its power system, its thermal architecture, everything about it is optimized for vertical descent through solid ice. The moment it breaks through the ice-ocean interface, it transitions from an environment it was built for into one it was not. The probe is now floating or sinking in liquid water, tethered by a communication cable to the ice above, surrounded by water in every direction with no visible reference point. Its instruments, whatever it carries, must now perform the science that justified the entire mission. And the question of what instruments to carry and where to point them is far from settled. The first strategic decision is directional. Does the probe explore the water column immediately beneath the ice-ocean boundary, or does it attempt to descend to the seafloor? Both options have compelling scientific rationale and severe practical constraints. The ice-ocean interface is scientifically interesting because it is the zone where material cycled down from the radiation process surface might mix with ocean water. Oxidants created by Jupiter's radiation bombardment of the surface ice, compounds like hydrogen peroxide and molecular oxygen, could be delivered to the ocean through geological processes that transport surface material downward. If these oxidants reach the ocean, they would react with reduced compounds dissolved in the water, creating chemical energy gradients that biology could exploit. The underside of the ice might host microbial communities analogous to the organisms that colonize the undersides of sea ice in Earth's polar regions. Sampling this interface zone requires no additional propulsion. The probe simply hangs at the boundary, extends its instruments, and collects data from the immediate environment. The seafloor, on the other hand, is where the most compelling energy sources for life are expected to exist. Hydrothermal vents, if they are present, would be located where heated water emerges from cracks in the rocky interior. These vents would represent concentrated sources of chemical energy and dissolved minerals, exactly the kind of environment where chemosynthetic ecosystems thrive on Earth. But the seafloor could be 60 to 150 kilometers below the ice-ocean interface. Reaching it from the entry point would require the probe to descend through the full depth of the ocean under its own power, navigating in total darkness without any prior mapping data. The energy cost of this descent and the time required to complete it might exceed the probe's operational lifetime. A tethered cryobot cannot realistically explore the full ocean depth. The communication tether connects it to the ice above. Descending to the seafloor would require either an impossibly long tether extension or severing the communication link entirely, which means any data collected at the seafloor would need to be stored internally, and the probe would need to somehow return to the ice boundary to transmit it. Neither option is practical with current or foreseeable technology. This limitation has inspired one of the most creative engineering concepts in the entire Europa exploration portfolio. A project at NASA's Jet Propulsion Laboratory called SWIM, which stands for Sensing with Independent Microswimmers, proposes a radically different approach to ocean exploration. Instead of sending one large probe to do everything, the concept envisions packing approximately 4 dozen tiny wedge-shaped swimming robots inside the cryobot alongside its other instruments. Each robot would be roughly 12 centimeters long, about the size of a mobile phone, with its own propulsion system, onboard computer, ultrasound communication capability, and a miniaturized sensor package capable of measuring temperature, pressure, salinity, acidity, and chemical composition simultaneously. Once the cryobot penetrates the ice and enters the ocean, it would release these micro-swimmers in waves. The robots would fan out from the entry point, each following autonomous navigation algorithms designed to chase chemical and thermal gradients. If a warmer plume of water indicates a hydrothermal source in one direction, the swimmers would follow it. If a chemical signature suggests biological activity in another, they would converge on the signal. Each swimmer would operate on battery power for approximately 1 to 2 hours before returning to the cryobot to transmit its data via short-range ultrasound. The cryobot would then relay the combined data set up through its tether to the surface. The swarm approach solves several problems simultaneously. It extends the exploration radius far beyond what a single tethered probe could achieve. It provides redundancy, because losing a few swimmers to malfunction or navigation errors does not end the mission. It allows simultaneous sampling of multiple locations, creating a three-dimensional map of ocean conditions around the entry point. And it dramatically increases the probability of detecting localized phenomena like hydrothermal plumes or biological hotspots that a single stationary probe might miss entirely. JPL engineers tested swim prototypes in a 23-meter competition swimming pool at Caltech in September of 2024, demonstrating that the tiny robots could navigate autonomously, communicate via ultrasound, and carry functional sensor payloads. Collaborators at Georgia Tech fabricated a multi-parameter ocean sensor chip just a few millimeters square that integrates temperature, pressure, pH, conductivity, and chemical sensing into a single package. Computer simulations suggested that a swarm of 12 robots deployed in 4 to 5 waves could collectively scan approximately 86,000 cubic meters of ocean volume, a meaningful sample of the environment near the entry point. The SWIM concept remains early stage. It is funded through NASA's Innovative Advanced Concepts program and is not yet part of any approved mission. But it represents exactly the kind of creative engineering that the Europa Challenge demands. The problem is too hard for a single monolithic system to solve alone. Breaking the exploration task into many small, expendable, semi-autonomous agents distributes the risk and multiplies the scientific return. The question of what to look for once instruments are in the water is itself a subject of active debate. Detecting life is not as simple as pointing a camera at the water and looking for fish. If biology exists in Europa's ocean, it is almost certainly microbial. Single-celled organisms, perhaps analogous to Earth's bacteria or archaea, existing at low densities in a cold, dark, nutrient-limited environment. Detecting such organisms requires instruments sensitive enough to identify molecular biosignatures at extremely low concentrations. Candidate biosignatures include amino acids with specific chirality, meaning a preference for left-handed or right-handed molecular configurations that biology produces but random chemistry does not. They include lipid molecules that form cell membranes, complex organic polymers that serve as information-carrying molecules analogous to DNA or RNA, and chemical disequilibria in the water that can only be maintained by active metabolism. Each of these signatures requires a different instrument: a mass spectrometer for molecular identification, a fluorescence microscope for detecting cellular structures, a Raman spectrometer for identifying mineral and organic compositions. Fitting all of these instruments into a probe that must also carry a nuclear reactor, a communication tether, navigation systems, pressure housings, and 4 dozen microswimmers is an integration challenge that makes spacecraft design look straightforward by comparison. And underlying all of this is a philosophical question that the engineering cannot answer. What if Europa's life, assuming it exists, uses biochemistry so different from Earth's that our instruments cannot recognize it? Every biosignature detection method currently proposed is calibrated against terrestrial biology. We search for the molecules that Earth life uses because those are the molecules we understand. If Europa's ocean has produced living systems based on fundamentally different chemistry, our instruments might register nothing at all. The probe could swim through a living ocean and report it as sterile, not because life is absent, but because we did not know what to look for. This uncertainty does not invalidate the mission. It sharpens it. The instruments must be designed to detect not just specific molecules, but anomalous patterns, chemical distributions that deviate from what abiotic processes would produce, energy gradients that should not persist without active maintenance, structural features in the water that resemble cellular organization, even if they do not match terrestrial templates. The search for life on Europa is not just an engineering challenge. It is a test of whether our understanding of biology is universal or parochial. Several research groups have built and tested terrestrial prototypes that address pieces of this challenge in isolation. NASA's Jet Propulsion Laboratory tested a probe called Valkyrie in the Matanuska Glacier in Alaska, demonstrating that a laser-heated melt probe could descend through glacial ice while maintaining a fiber optic tether. The German Aerospace Center developed and tested the Ice Mole probe, a hybrid melt drill device that demonstrated directional steering within ice. Stone Aerospace in Austin, Texas, has developed a series of autonomous underwater vehicles designed for under-ice exploration and tested beneath Antarctic ice shelves. The British Antarctic Survey has deployed hot water drilling systems that can penetrate hundreds of meters of Antarctic ice in hours. Each of these projects validated specific elements of the Europa challenge. Melting works. Tethers can be maintained over meaningful distances. Autonomous navigation beneath ice is achievable. But every one of these tests operated in conditions profoundly more forgiving than what Europa presents. Terrestrial glacial ice sits at temperatures only modestly below freezing, not 160 degrees below. Antarctic ice shelves are hundreds of meters thick, not tens of kilometers. Terrestrial prototypes operate with human oversight, backup power, and the option to abort. On Europa, there is no abort. There is no backup. There is only the probe, its power source, and kilometers of ancient ice between it and the ocean. The gap between terrestrial ice penetration and Europa ice penetration cannot be bridged by incremental improvement to existing technology. It requires fundamental advances across multiple engineering domains simultaneously. Compact nuclear power systems must be developed that fit within a narrow cylindrical body and operate autonomously for years. Communication systems must be created that transmit data reliably through kilometers of heterogeneous ice. Autonomous navigation and hazard avoidance algorithms must be validated for environments that cannot be fully replicated in any laboratory on Earth. Sterilization and verification methods must achieve contamination probabilities lower than anything previously demonstrated for flight hardware. Pressure vessels and instruments must be qualified for ocean conditions that remain largely hypothetical. Each of these advances constitutes a major engineering program in its own right, requiring years of dedicated research, development, and testing. Combining them into a single integrated system that must function flawlessly from surface touchdown through ice descent, through ocean entry, through scientific investigation, all without a single human being available to intervene at any point, represents a challenge that stands at or beyond the current frontier of what human technology can accomplish. Some mission architects have proposed alternatives that reduce the engineering burden by lowering the scientific ambition. One concept focuses on finding regions where the ice may be exceptionally thin, perhaps only 2 to 3 kilometers, and targeting those locations for a shorter, less demanding descent. But identifying these thin spots requires orbital reconnaissance data that Europa Clipper has not yet collected, and even a 2-kilometer descent through Europa's cryogenic ice with an autonomous nuclear-powered probe trailing a fiber optic tether through refreezing melt channels represents an achievement without precedent. Another concept sidesteps ice penetration entirely by searching for ocean material that natural geological processes have already delivered to the surface. If recent cryovolcanic eruptions or tectonic disruptions have deposited fresh ocean-derived material on the ice, a surface lander might detect biosignatures without drilling deep at all. This approach dramatically reduces engineering risk but accepts dramatically reduced scientific confidence. Surface material exposed to Jupiter's radiation may have lost whatever biological signatures it once carried, and there is no guarantee that recent ocean-derived deposits exist at any accessible landing site. The engineering community working on Europa ice penetration understands all of this with clear-eyed precision. They are not deluded about the magnitude of the challenge. They are not promising timelines they cannot keep. What they are doing, methodically and patiently, is developing the individual technologies that will eventually need to come together into an integrated system. Testing melt probes in progressively more challenging ice environments, developing fiber optic tethers with better strength-to-weight ratios, designing compact fission reactors with higher power densities, writing autonomous navigation software and validating it in underwater testbeds beneath polar ice, advancing sterilization techniques and pushing bioburden verification to higher confidence levels. None of this work will produce a flight-ready Europa cryobot tomorrow, or next year, or likely within the next 2 decades. But it is laying the foundation for a capability that did not exist 10 years ago, and that will be substantially more mature 10 years from now. The engineering of ice penetration is advancing on a timeline measured in decades, driven by incremental progress across a broad front of enabling technologies. The question that remains is not whether ice penetration is physically possible. The thermodynamics work. The physics permits it. The question is how long it will take to convert theoretical feasibility into operational reality. And that question leads directly into the final dimension of the Europa story, the one that confronts the human element. Timelines that span careers, missions that span generations, and an ocean that will not reveal itself to anyone who arrives unprepared. Europa Clipper is already on its way. Launched in October of 2024 aboard a SpaceX Falcon Heavy rocket, the spacecraft is tracing a long curved path through the inner solar system, collecting gravitational energy from Mars and Earth before angling outward toward Jupiter. If everything proceeds as planned, it will arrive in the Jupiter system around 2030, 6 years after leaving the launch pad. When it gets there, it will not settle into orbit around Europa. That would be suicide. Instead, the spacecraft will orbit Jupiter itself on a carefully designed elliptical path that periodically swoops close to Europa before retreating to the relative safety of Jupiter's outer magnetosphere. Each of these close encounters, approximately 49 planned over the primary mission phase, will carry the spacecraft within as close as 25 kilometers of Europa's fractured surface. At closest approach, Europa Clipper will be moving at roughly 4 kilometers per second relative to the Moon, crossing from horizon to horizon in minutes. During each brief flyby window, every instrument on board must execute a pre-programmed observation sequence with split-second timing. Cameras will photograph surface terrain at resolutions approaching 0.5 meter per pixel. Spectrometers will map the chemical composition of the ice, searching for organic molecules, salts, and compounds that may have originated from the ocean. A thermal imager will measure surface temperatures, identifying anomalously warm regions where heat from below may reach closer to the surface. A magnetometer will refine the measurements that Galileo first made, constraining the ocean's depth, conductivity, and global extent with far greater precision. But one instrument aboard Europa Clipper carries significance that outweighs all the others for the long-term goal of ocean access. Reason, the radar for Europa assessment and sounding, ocean to near-surface instrument, is an ice-penetrating radar system designed to peer beneath the surface. By transmitting radio pulses downward and listening for echoes returned from subsurface interfaces, Reason can potentially detect the boundary between the ice shell and the liquid ocean below. It can identify variations in ice thickness across the surface. It can reveal internal layering, brine pockets, and structural discontinuities within the shell. If thin spots exist, regions where the ice measures only a few kilometers rather than 20 or 30, Reason is the instrument most likely to find them. The data from Reason will not tell us what lives in the ocean. It will not confirm whether hydrothermal vents exist on the seafloor. It will not resolve the question of whether Europa harbours biology. What it will do is transform the ice shell from an almost complete unknown into a mapped geological structure with measured properties, and that transformation is the prerequisite for everything that follows. You cannot design a drilling mission to a target whose depth, composition, and internal structure you do not know. Reason provides the blueprint. Without it, every ice penetration concept remains a thought experiment untethered from measured reality. Europa Clipper will also provide critical data for landing site selection. High-resolution imaging will reveal surface hazards, boulder fields, crevices, steep slopes, and regions of unstable terrain that could destroy a lander on contact. Topographic mapping will identify flat, stable areas where a spacecraft could safely touch down. Compositional mapping will highlight regions where ocean-derived material may be most accessible on the surface. Thermal measurements will constrain where heat flow from the interior is highest, potentially indicating locations where the ice is thinnest or most recently disrupted. All of this data feeds into the design of the next mission in the sequence, a Europa lander. NASA's Jet Propulsion Laboratory has studied a lander concept extensively, producing detailed mission architectures that describe a solar-powered spacecraft designed to operate on Europa's surface for approximately 20 to 30 days. The lander would carry a suite of instruments focused on one central question: are there signs of life in Europa's near-surface ice? The instrument suite envisioned for the lander concept includes a microscope capable of imaging structures at cellular scales, an organic molecule analyzer that can detect amino acids, lipids, and other compounds associated with biological processes, and a vibrational spectrometer that identifies molecular bonds characteristic of biological chemistry. The lander would collect ice samples from the upper few tens of centimeters of the surface, where material may have been deposited by geological processes cycling ocean water upward through the shell. But the Europa lander has not been formally approved or funded as of today. It exists as a studied concept, a detailed engineering blueprint waiting for a political and budgetary decision that could come in the next few years or could be deferred for a decade or more. The scientific community has advocated strongly for the mission. The National Academy's Planetary Science Decadal Survey has identified Europa as a priority target. But advocacy and priority do not automatically translate into appropriated dollars, signed contracts, and hardware on a launch pad. If the lander is approved in the early 2030s, a realistic development timeline would place the launch in the late 2030s or early 2040s. Add 5 to 7 years of transit to Jupiter, and the lander would arrive at Europa in the mid-2040s at the earliest. This means the first direct contact between a human-built instrument and Europa's surface ice could occur approximately 2 decades from now. 2 decades of waiting after Europa Clipper's arrival. 2 decades of analyzing orbital data, designing landing hardware, testing instruments, qualifying systems for the radiation environment, and navigating the political process that allocates funding for flagship missions. 2 decades is an optimistic estimate. Budget constraints, technical delays, shifting political priorities, and the inherent complexity of flagship-class mission development could easily extend the timeline. The James Webb Space Telescope was first proposed in 1996 and did not launch until December of 2021, a 25-year arc from concept to flight. The Mars Science Laboratory mission, which delivered the Curiosity rover, took approximately 11 years from initial concept studies to landing. Europa's lander, operating in a far more hostile environment with far more stringent planetary protection requirements, could easily match or exceed these development timelines. And the lander, even if everything goes perfectly, does not reach the ocean. It scratches the surface. It analyzes whatever material exists in the top meter of ice. If that material contains detectable biosignatures, the scientific case for a subsurface mission becomes overwhelming. If it does not, the result is ambiguous. Absence of evidence on the surface is not evidence of absence in the ocean. Radiation processing could destroy biological molecules in surface ice. Ocean material might not reach the surface at any accessible location. A negative result from the lander does not close the question. It merely confirms that the surface cannot answer it, and that going deeper is the only path to resolution. The progression from lander to subsurface probe represents the steepest technological step in the entire sequence. The orbiter to lander transition is challenging, but bounded by existing engineering heritage. Spacecraft have landed on the Moon, Mars, Venus, Titan, a comet, and an asteroid. The physics of descent and touchdown is well understood. Radiation hardening and autonomous operations are demanding, but achievable with current technology extended to higher performance levels. The lander to subsurface probe transition is different in kind, not just in degree. Nothing in the history of space exploration provides direct heritage for a nuclear-powered autonomous vehicle descending through kilometers of extraterrestrial ice into a pressurized alien ocean while maintaining communication through a refreezing medium and satisfying planetary protection constraints that exceed anything previously attempted. The technology development required for a Europa cryobot mission spans multiple independent engineering domains. Compact fission reactors suitable for integration into a probe body must be designed, built, tested, and flight qualified. This process alone, from concept through ground demonstration through space qualification, typically spans 15 to 20 years for nuclear systems, which face additional regulatory hurdles related to the launch of radioactive materials. Communication systems capable of transmitting data through kilometers of ice, whether fiber optic tethers, acoustic relays, or some yet-to-be-developed approach, must be matured from laboratory prototypes to flight-ready hardware. Autonomous navigation algorithms must be validated in progressively more realistic test environments, culminating in full-scale trials in terrestrial ice analogues that approximate Europa's conditions as closely as possible. Each of these technology development paths is already underway at various institutions around the world. NASA's Kilopower program demonstrated compact fission reactor technology in ground tests. The German Aerospace Center and several European universities are testing ice-penetrating probe prototypes in alpine and polar glaciers. Autonomous underwater vehicle technology is advancing rapidly, driven by both scientific and commercial applications in Earth's oceans. The individual building blocks are being developed, but integrating them into a coherent, flight-qualified system remains a task for the future. Realistic projections for a Europa subsurface probe mission place the earliest possible launch in the late 2050s or 2060s. Some planetary scientists privately suggest that the 2070s or even 2080s may be more realistic, depending on the pace of technology maturation and the availability of funding. These timelines sound discouragingly distant, but they reflect an honest accounting of what is required, rather than an optimistic narrative designed to maintain public enthusiasm. The total arc of Europa ocean exploration, measured from Europa Clipper's launch in 2024 to a hypothetical probe making first contact with liquid water beneath the ice, could span 40 to 70 years, an entire human career, possibly two. The scientists who designed Europa Clipper's instruments, who wrote the proposals, who fought for the funding, who built and tested the hardware, may not live to see the mission that their work ultimately enables. Graduate students analysing Clipper's radar data in the early 2030s will be approaching retirement before a subsurface probe could plausibly return results. The engineers who will eventually build the cryobot that reaches the ocean may be children today, or may not yet be born. This multi-generational timescale is not unique in the history of ambitious human projects. Medieval cathedrals took centuries to complete. The architects who designed the foundations knew they would never see the spires. The stonemasons who carved the lower walls understood that their grandchildren might lay the upper courses. The project transcended individual lifetimes because the community that sustained it valued the goal more than any single contributor's desire to see it finished. Scientific exploration has its own cathedral projects. The measurement of stellar parallax, first attempted in antiquity, was not achieved until 1838. The confirmation of continental drift, proposed in 1912, was not accepted until the plate tectonics revolution of the 1960s. The detection of gravitational waves, predicted by Einstein in 1916, required a century of incremental technological development before LIGO succeeded in 2015. Europa's ocean belongs in this category. The goal is identified, the destination is confirmed, the scientific motivation is overwhelming, but the means of access require technological capabilities that must be built across decades of sustained effort, handed from one generation of engineers and scientists to the next, each cohort advancing the state-of-the-art a little further toward the threshold of feasibility. This reality creates a distinctive psychological and institutional challenge. Space agencies must maintain programmatic continuity across political administrations that change every 4 to 8 years. Funding bodies must commit to technology development programs whose payoff lies beyond the planning horizons of any budget cycle. The scientific community must train successive generations of researchers who are motivated by a goal they may never personally achieve. Public support must be sustained for a mission whose most dramatic moment, the first contact with an alien ocean, lies decades in the future and is not guaranteed to occur at all. The history of space exploration provides both encouraging and cautionary examples. The Voyager program, conceived in the late 1960s, continues to return data more than 4 decades later, sustained by a small but dedicated team at JPL. The Hubble Space Telescope, plagued by early failures and budget overruns, became one of the most productive scientific instruments in history through sustained institutional commitment. The Mars exploration program has maintained a cadence of increasingly capable missions across 3 decades, building systematically from simple orbiters to complex rovers. But history also records ambitious programs that were cancelled, deferred, or abandoned when political will faltered. The superconducting super collider, partially constructed in Texas, was cancelled in 1993 after billions of dollars had been spent. NASA's Constellation program for crewed lunar exploration was cancelled in 2010 after 5 years of development. The Europa mission itself was proposed, studied, deferred, revived, renamed, and restructured multiple times over 2 decades before Europa Clipper finally received approval and funding. Sustaining the Europa exploration program through its full multi-decade arc will require something that space agencies have rarely achieved: continuity of purpose across a timeline longer than any individual career. International collaboration could help. The European Space Agency's JUICE mission, launched in April of 2023 and arriving at Jupiter in 2031, will study Europa during 2 planned flybys before entering orbit around Ganymede. JUICE carries its own ice-penetrating radar and a suite of instruments that will complement Europa Clipper's observations. Sharing data between NASA and ESA strengthens the scientific foundation for future missions while distributing the cost and risk across multiple space agencies. Other international partners could contribute to later phases of the program. Japan's space agency JAXA has experience with autonomous landing systems from its asteroid sample return missions. The German Aerospace Center leads some of the most advanced cryobot development programs in the world, collaborative frameworks that allow multiple nations to contribute technologies, funding, and expertise could accelerate the timeline and build the kind of broad institutional support that protects long-duration programs from the budget fluctuations of any single nation. Private sector technology development offers another potential accelerator. Companies developing compact nuclear reactors for terrestrial power generation are advancing miniaturization and safety technologies that could be adapted for space applications. The autonomous underwater vehicle industry is growing rapidly, driven by offshore energy, military and oceanographic applications, and the navigation and sensing technologies it produces are directly relevant to a Europa subsurface probe. Fiber optic communication systems are advancing continuously, driven by the telecommunications industry's insatiable demand for bandwidth. Cross-pollination between commercial technology development and space mission engineering could reduce both the cost and the timeline for developing Europa-specific capabilities. But no amount of collaboration or commercial partnership can eliminate the fundamental seriality of the exploration program. Each mission must fly, before the next can be designed. Europa Clipper must return its radar data before a lander mission can select its target. The lander must characterize the surface before a subsurface probe can be engineered. The subsurface probe must demonstrate ice penetration before an ocean explorer can be built. This sequence cannot be parallelized. Each step depends on the results of the one before it. Attempting to skip ahead, to design a cryobot before the ice shell has been mapped, risks building a probe for an environment that turns out to be radically different from the assumptions that guided its design. The consequence of that error would not be a minor setback. It would be the loss of a multi-billion-dollar mission and a decade or more of wasted effort. The scientific patience required for Europa exploration stands in tension with a culture that celebrates speed and disruption. The popular narrative of space exploration emphasizes bold leaps. Kennedy's moonshot commitment, the 8-year sprint from presidential speech to lunar landing, the dramatic rover landings on Mars, executed in minutes of autonomous terror after years of preparation. These stories are inspiring because they compress decades of effort into moments of climactic achievement. They create the impression that space exploration proceeds through audacious singular acts, rather than through the slow accumulation of capability across generations. Europa does not fit this narrative. There is no single bold leap that carries humanity from ignorance to discovery. There is only a long, methodical campaign of reconnaissance, characterization, technology development, and incremental extension of reach. The dramatic moment, if it comes, will arrive not as the culmination of an 8-year sprint, but as the final step in a 50-year march. The probe that first touches Europa's ocean will carry within it the legacy of every mission that came before, every orbital measurement, every surface sample, every failed prototype, every engineering lesson learned through decades of patient work. There is something profound in this patience. The ocean beneath Europa's ice has existed for approximately 4.5 billion years. It predates the emergence of life on Earth. It predates the formation of Earth's moon. It has persisted through the entire history of the solar system, maintained by the same tidal forces that cracked its ceiling open and froze it shut again in cycles spanning millions of years. Whatever exists in that ocean, whether it is simple chemistry, complex organic molecules suspended in cold salt water, or something that crosses the threshold into what we would recognize as alive, it has had time beyond human comprehension to develop. Against that timescale, the decades required for human exploration are nothing. They are the last few seconds of a clock that has been ticking for billions of years. The urgency that scientists feel, the desire to know whether we are alone, the hope that Europa might harbour the most important discovery in human history, is real and valid. But it must be tempered by the recognition that the question deserves an answer obtained correctly, not merely quickly. A rushed mission that fails, that crashes on landing because the surface was not adequately mapped, that deploys a cryobot into ice twice as thick as its power source can sustain, that contaminates the ocean with terrestrial microbes because sterilization protocols were compressed to meet a political deadline, would be worse than no mission at all. It would waste resources, destroy scientific credibility, and potentially set back the program by decades. The ocean can wait. It has been waiting since before there were human beings to wonder about it. What it cannot survive is carelessness. The European Space Agency captured something essential when it named its Jupiter mission JUICE, the Jupiter Icy Moons Explorer. The name is playful, but the mission philosophy behind it is serious. Explore first, understand the environment, map the territory, build the knowledge base that makes the next step possible. Do not rush toward the prize. Earn the right to reach for it through disciplined, systematic investigation. This philosophy must guide the entire Europa program. Clipper maps, the lander characterizes, technology programs, mature. And eventually, when the engineering is ready and the knowledge is sufficient and the institutional commitment has been sustained long enough, a probe descends through ice that was first mapped decades earlier, into an ocean whose existence was first confirmed by a spacecraft named after a Renaissance astronomer who pointed his telescope at Jupiter 4 centuries ago. The distance between Earth and Europa is approximately 588 million kilometers at closest approach. A spacecraft can cross that distance in 3 to 7 years. The ice between Europa's surface and its ocean is perhaps 5 to 30 kilometers thick. A probe might need 1 to 4 years to melt through it. The distance is vast. The ice is comparatively thin. But the ice is harder to cross than the void of space itself, because space, for all its emptiness, is a medium we understand. We have sent spacecraft through it for 60 years. We have navigation techniques, communication protocols, propulsion systems, and operational experience accumulated across hundreds of missions. The ice is different. We have never sent anything through kilometers of extraterrestrial ice. We have no operational experience, no flight heritage, no proven technology. We have concepts, prototypes, calculations, and confidence that the physics permits what the engineering has not yet achieved. That gap between physical possibility and engineering reality is the true distance to Europa's ocean. And it is measured not in kilometers or in years of travel time, but in decades of disciplined technological development. Europa is not far, it is deep. And deep, in this context, means something more than physical depth beneath a layer of frozen water. It means depth of commitment, depth of patience, depth of the sustained institutional will required to pursue a goal whose full realization lies beyond any individual human lifetime. The ocean is there, the water is real, the chemistry is promising, the scientific question is among the most important humanity has ever formulated, and the answer is locked beneath a shell of ice that has guarded it since the formation of the solar system. We will reach it, not with a single bold mission, not within a single decade, not within a single career, but through the accumulated effort of generations of scientists and engineers, each one advancing the frontier a little further, each one handing the work forward to those who come after. The probe that finally breaks through the last meter of ice and enters that dark, ancient ocean will carry the legacy of every mission, every prototype, every failed experiment, and every hard-won insight that preceded it. That is what it would really take to explore Europa. Not 6 years of travel, not 30 days on the surface, but decades of patience, generations of commitment, and the willingness to pursue a goal whose importance justifies the extraordinary timescale required to achieve it. The ocean has waited 4.5 billion years. It can wait a little longer for us to arrive properly.